Hello everyone, let's talk about the Coriolis effect. Now this concept and theory in atmospheric science and also geography is quite complex. There's two parts to it, inertia and angular momentum, but usually you only learn about this part, and this video goes in depth about this one as well, which is an important component of the Coriolis effect. This video goes in a lot of depth and you don't really need it if you're studying for an examination like A-levels, but I think it's just good knowledge to have overall. So let's start by defining what the Coriolis effect is. So it's defined as the apparent deflection of moving objects on a rotating body. If we're talking about the atmosphere, our moving object is the air and our rotating body is the earth. Now, let's put it on a diagram. We know from science that air moves from high pressure to low pressure. In colder areas, you have air sinking down, so there's a high pressure on the land, whereas in warmer areas, there's air moving and rising up, and therefore you have a low pressure. A vacuum can't exist when air is rising, so air has to come in to fill that gap, and that air comes from high pressure areas. So in theory, what this should mean is, at high pressure areas, it should move up towards low pressure areas. It should move something like a straight line. But what actually happens is something like this. There's a deflection, and that is the Coriolis effect, because we are rotating somewhere. And this Coriolis effect has large impacts around the world with things such as trade winds. So let's move into the explanation. Imagine a globe like you have over here, and usually you are used to looking at it at the equator, but now flip it over so that you have the North Pole, or one of the poles at least. So let's put a dot over here. And your circle, your circumference, is now the equator. Because we know the Earth is rotating towards the east and spinning towards the east, if we look at our North Pole, it's going to spin anti-clockwise. So something like this. Now, recall the formula for speed. Speed, or v, equals distance over time. And let's have something fixed to compare. Let's measure the time for which the Earth makes one rotation, which is 24 hours. So we can write time, or t, as 24. So now we see that this velocity or speed and distance are directly proportional. So whatever is higher, the other is higher. So we can see here a higher distance means a higher velocity. And now let's go back to our diagram. You can see around the equator, to make one rotation in 24 hours, it has to move that much distance. The equator is large, the whole circumference of the Earth, and therefore you have high speed. Whereas if you're at the North Pole, you don't have to move at all, and you just make one rotation. So your velocity is 0. If you go out a bit from the pole, you have something like this. It's still moving anti-clockwise in the northern hemisphere, but now you can compare much more easier. This circle is much smaller than this circle, and they all have to move from this point back to this point and this point to this point in 24 hours. So it has to travel at much more faster speed around this circle, the equator, than nearer to the pole, because of our equation over here. And then we can put this on a map. I'm not going to draw the continents because it's gonna look bad. That's why I don't take art. But with our northern hemisphere here, southern hemisphere here, because air is moving faster around the equator, we can visualize this with kind of 3 arrows. Say it's moving very fast, whereas towards the pole, it's moving with 1 arrow and much more slower. So let's ignore things such as the ferrocell because that complicates things. Let's just look at the pole as somewhere with cold temperatures and therefore high pressure, and the equator as somewhere with low pressure because it's warmer, right? So low pressure here and high pressure at the poles. Therefore, in theory, the air should move like this, from high pressure to low pressure. But remember, our speed here is quite low. It's moving at a lower speed. And when it travels down, it's going to maintain that speed because of inertia. right? It's difficult to change that speed because you're already moving at that speed. What this means is you're going to trail behind the speed, the air that's moving faster. Imagine you're driving a car in a slow lane and you're going to change lanes into a faster lane, but you maintain the speed at which you are driving in the slow lane. So it's going to look like cars that are driving in the faster lane are going to pull ahead of you. So in which case you're going to tail behind other cars, and you're on a flat map, you're going to look something like this. You see there's a deflection there. Similar here, you're moving slower than the air here, so you're going to look like you're tailing behind the air. If for some reason air travels the opposite direction, so towards the north like that and towards the south like that, then remember you have fast air here and slow air here. If you're faster than the slow air, then you're going to pull ahead of cars or air. So it's going to look something like this. You're pulling ahead of the air because you're moving faster. And as you can see, that is the Coriolis effect. Over here, same thing over here. And to make it simpler for you, just think about the direction you're moving. You're going to move right in the northern hemisphere and left in the southern hemisphere. So you can see here, it's going to move down, theoretically down, and therefore it's right side. It's going to move up, and that's the right side. In the southern hemisphere, it's going to move up, and then that's going to be the left side. If it's going to go down, then it's going to be the left side. So remember, north, right, south, left. But that's not all. It's not just inertia, and there's something about angular momentum as well. Angular momentum is something's turning this. You don't have to understand it, but just know that there are two components of it. You have your distance from axis, so your distance from your spinning area, which is the North Pole or the poles, and you also have your speed. And in physics, higher distance from the axis means higher angular momentum, and higher speed or higher velocity equals higher angular momentum. Now you can quickly see that around the equator, it's very far from the axis, and therefore it's gonna have a high angular momentum. So let's write that down. At equator, high angular momentum. And when you're closer to the poles, your distance decreases, therefore you have a lower angular momentum. Lower distance. And then lower angular momentum. But we know that momentum has to remain the same before and after. So when air is moving from here to here, the momentum has to stay the same. But obviously our distance will start to increase as we're moving towards the equator. And therefore, our angular momentum should increase. That can't happen. And something has to change to offset that increase in angular momentum. And that is your velocity. So as you're moving towards the equator, your distance increases. So theoretically, your angular momentum should be higher. But your angular momentum has to stay the same with physical laws. And therefore, your velocity will change and your velocity has to decrease. And therefore, your angular momentum decreases. So as you're moving towards the poles, your speed actually decreases. So let's write that down. So moving towards the equator. And that's vice versa. If you're moving towards the poles, your speed increases. So now let's put this on our map again. Fast arrow over here. And slower arrow over here. So with this, your normal calculations are like this. And then if you're going to go in the opposite direction, but because you're going to slow down as you move towards the equator, then you're going to trail even more behind. And therefore, you're going to actually be like this. So it's going to end up in a further back position. And same for over here. And then because you're going to gain velocity, gain speed as you move towards the poles, you're going to pull ahead even more. So So you're going to be somewhere over here. So as you can see, with the angular momentum calculation, you're going to be in a further point than you would have predicted. And that's why when people like Hadley and Coriolis were figuring out this and using the math to predict the Coriolis effect, they often ended up over here because they didn't account for angular momentum. When you do account for angular momentum, your speed decreases or increases, and therefore you're going to have a greater effect. So these two things sum up the Coriolis effect. It's quite complex. If you have any comments, leave it down in the comments. I'll answer you. But hope you guys understand now, and I'll see you in the next one.